Many of us, including me for a long time, heard this explanation for Heisenberg Uncertainty Principle. Imagine you want to measure a tiny electron, you shine a light on it to see where it is, but that light kicks the electron, changing its speed. So the act of measuring its position disturbs its momentum. Well, you can say that why not use a light with lower energy? But then that will increase the wavelength and hence our ability to pinpoint position of said particle, in our case electron. The problem with this statement is that this is not Heisenberg's uncertainty principle. Werner Heisenberg himself said that this might be a possible cause for the uncertainty principle. The underlying principle itself, though, is much more deeper and satisfying. It all starts with the wave-particle duality. You must have heard that everything in our universe behaves like a particle and a wave. What people get it confused with is that they think that quantum objects are both a particle and a wave. No, they are not. Their behavior has some traits of particle and some traits of wave. It does not mean that they are either or both. In the late 19th century, we started having some issue with the definition of light as electromagnetic wave. Problems like ultraviolet catastrophe, where this electromagnetic wave nature of light was unable to explain blackbody radiation. Then came along clever people like Einstein and Max Planck. They showed that light exhibits particle behavior too and must come in packets, which Einstein called light quanta in 1905, later called photons. This solved the issues and experiments which the electromagnetic nature of light was not able to explain. Furthermore, Max Planck gave an equation for the energy a photon packet can have, and from here turned out that for a wave its momentum and wavelength are related. Let me know in the comments if you want the derivation. And just like we had issues explaining some experiment with the electromagnetic behavior of light, we had issues explaining atoms if we considered electrons as point particles. You see, electron has charge, and to be able to move on a circle even with constant speed, your velocity must change since your direction is changing. And as we know, if a charged particle accelerates, it emits electromagnetic radiation and thus loses energy. That means electrons should simply lose energy and collapse in the nucleus. Hence, as per classical mechanics, atoms should not exist. But clearly they do. People hypothesized different models to stabilize atoms. For example, this Bohr's model, which failed to explain a lot of stuff about atoms. So then comes a guy named Louis de Broglie, and he suggested that if light, which we thought to be an electromagnetic wave, can have particle-like characteristics, why not electrons, which we think to be particle, can have wave-like characteristics? Notice that it does not mean that photons and electrons are either particles or waves or both. Now, there is a fundamental issue with something having both particle and wave characteristics. Let's see how. Imagine that you are a particle. By definition, a particle exists in a single point in space at a given instance in time. However, if you are a wave, by definition, you are a disturbance which spreads throughout the space at any given instance in time, like a ripple in a water body. If I ask you what is the wavelength of this wave, you can easily get the distance between any two consecutive peaks or valleys. That's the wavelength. But what's its position? We don't know. This wave goes like this till infinity. So it can be anywhere and everywhere. But why infinity? Why not like this? I mean, this way we can be sure that position will be somewhere here. But you see, that's not correct. So here the wavelength have a finite value. But what about here? It has been changed. Here the wavelength is infinite. So if you have a fixed wavelength of a wave, which is closely related to its momentum, that means you do not have its position. But hang on, if everything has a particle and a wave nature, how come we know the exact position of our everyday objects? Remember this: if an object is moving fast or is heavy, it has a lot of momentum and thus extremely tiny wavelength. And that's why we don't notice this dual nature of everyday objects. However, for small things like electrons, suddenly this wavelength becomes significant, and thus we see the dual nature. But we know that the electrons are present in the atom and not spread throughout the whole universe. So, can we work our way towards our electron having a definite position? We can do that by localizing the wave in a small area. That means we need to make the amplitude 0 or approx 0 at most of the positions and keep the amplitude at some of the positions. We can achieve this by adding waves with different phase. So at some place the peaks line up and interfere constructively, meaning they add up, and at some places they line up with valleys, interfere destructively, meaning they cancel out each other. Let's now try to improve our location certainty. So similarly, we add waves. So now our electron can exist anywhere here. But what if we want this uncertainty in position to reduce even more? We need to add more and more waves with increased frequency to make it narrower and narrower. As you can see, it looks impossible to make it exactly at one position. It retains at least some width, meaning at least some uncertainty in position. But let's say we are happy with this uncertainty. We say our electron is pretty localized now. But what you haven't realized is in doing so, we had to add so many different waves with so many different wavelengths and thus so many different momenta. Meaning you can find your electron corresponds to any one of those wavelengths which we added, and thus any one of those different momenta. So now you lost certainty in both position and momentum. Here, if you want to narrow down your uncertainty in position, you will have to add more waves with different momenta, and thus uncertainty in momentum will be increased. If you want to increase your certainty in momentum, you cannot have so many different waves with different wavelengths, meaning your wave will be less localized, so more uncertainty in position. This is Heisenberg Uncertainty Principle. As you saw, it has nothing to do with how we are performing our measurements. Rather, it is a limit on how much information we can have about a quantum object. In quantum mechanics, exact position and exact speed of a quantum object has no meaning. Are you convinced that quantum object is neither wave nor particle and not both? No, there are two ways. One of them is to learn and understand the math behind it, which can be pretty challenging, and that's why I partnered up with Brilliant, this video's sponsor. Brilliant is an online learning platform that helps you build the deep intuitive understanding of math, moving past memorization and into genuine insights. They have so many amazing courses in math, which it starts pretty basic but goes in depth on the topics. I absolutely fell in love with Brilliant's course on calculus. They don't just show you formulas, they use visual interactive lessons to help you see why a concept works. You will engage with hands-on problems that make everything from rate of change, derivative to area and volumes. And the amazing thing is that you can learn all these directly on your phone, which makes it easier for you to keep the momentum going on daily learning. If this sounds amazing and you want to try Brilliant out, you have free trial. Go to this link or scan this QR code to get 20% off of your annual premium subscription. Thank you Brilliant for sponsoring this video. And the second way is with intuition, which you will absolutely love and can check it out here.